So welcome back, everybody. I'd kind of finished up with my discussion of Fermat last time. What is left before the next block of 17th century mathematicians that will bring us into the 18th century once we're done discussing them. I hadn't talked about Pascal yet. It was kind of the last of this block that I wanted to mention. So Pascal... So his first name. Let me see if I have his dates of. Yeah, so he was born in 1623, died in 1662. Pascal was originally, as a kid, forbidden from studying math at all. Despite this, he had kind of like on his own, with no instruction, had worked through a lot of basic geometric facts and had basically rediscovered a lot of theorems from the elements. And so eventually, I believe his father, I think by the time he was 12, had given him a copy of Euclid's Elements so that he could actually learn more from it. So at age 14, he started going to meetings of other mathematicians, and this included Mersenne. This began, he wrote to Mersenne frequently. So as I said at the very beginning of this block, Mersenne is kind of like the glue holding together all these various French mathematicians, in that he corresponded with every single one of them. When Pascal was 16, he wrote a little article on conic sections, which contains what's called Pascal's theorem that I'm going to talk about here in a second. By the time he was 18, he had constructed a calculating machine, which is usually considered like the precursor to the actual first computer. There's even a programming language named after him. At around age 27, he completely gave up mathematics entirely and devoted himself to religious study. He would periodically return to math in his later life, every now and then, but for the most part, all of his mathematical contributions were done. But it's in some of this writing in this period that some of his philosophical questions are mentioned. So I'll talk about a little bit about those here in a second as well. So first I wanted to mention Pascal's theorem, and you will immediately notice something about it. So this he showed while he was 16 in his article on conic sections. So this is if a hexagon is inscribed in a conic, the points of intersection of opposite sides assumed to be non-parallel lie in a straight line. So this might be kind of hard to envision just like this. So it turns out that if we can prove it for a circle, we can actually prove it for any conic, and I'll talk about why that is here in a second, but here's what the picture looks like. So there's the picture. So the hexagon itself isn't drawn in here, much like in Pappus's hexagon theorem. The hexagon itself is not drawn in, but you could draw it in if you wanted to. You connect these six vertices together. So imagine you have an inscribed hexagon in this way. Okay, then these points of intersection from connecting these opposite vertices in this way are collinear, right? So where have we seen that before? Where have we seen something very similar? I already spilled the beans a little bit. This is a generalization of Pappus's theorem. So this is a generalization of Pappus's hexagon theorem. And to get Pappus's hexagon theorem out of this, what one has to do is rather than your rather than these vertices lying on a conic or on a circle, like in this picture, they actually lie on two lines that are non-parallel, right? So the degenerate, if you think of two non-parallel lines in that way as being a degenerate form of conic, which there's a way to do that, then this generalizes Pappus's theorem. And so this is actually a theorem in projective geometry. So this is our next theorem in projective geometry, which is really just a generalization of Pappus's hexagon theorem. So he did this when he was 16. So it's pretty nice, pretty impressive. So what is maybe the thing that you associate to Pascal more than anything, however, is Pascal's triangle. So even non-mathematicians, non-students of math, are likely familiar with Pascal's triangle. And so how do I form Pascal's triangle? So I begin with 1, I begin with my next row of 1, and then the outer layer is 1s, but the inner layer is determined by summing the two entries above to the left and right? So 1 plus 1 is 2. There we go. So this is a 1. 1 plus 2 is 3. 2 plus 1 is 3. Then I have a 1 here. Here's a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. I have a 1 here. Let's just do one more time. So 1 plus 4 is 5. 6 plus 4 is 10. 6 plus 4 is 10. 4 plus 1 is 5. I have a 1 on the outside. Okay, so this is how Pascal's triangle goes. It doesn't stop. You can keep going as long as you want to. All right, so there it is. Now, Pascal was not the first person to come up with this triangle. In fact, as we already said previously, this was due to the Chinese. There is, in that info dump, there is one of those links, and I can't remember it off the top. I can't remember the title off the top of my head, but one of those links, like when you click on it, the first thing it shows for that work is a very nice picture in Chinese of a figure that looks exactly like this, because that is indeed exactly what it is. So it is a Chinese drawing of Pascal's triangle that was written in like the 800s, I think. It may have even been a little bit earlier. But so Pascal was not the one who came up with this idea of this triangle, but he is the first that showed all the various properties that this thing has. So in the Chinese work, this triangle is computed, but nothing much else is done with it. So what is important? So what did Pascal show? So Pascal showed the following, that if you wanted to compute a single entry here in this table, wherever, maybe really, really far down, right? So the idea here was that you had rows, and these rows were labeled by n levels. So there's the n equals 0 level, there's the n equals 1 level, there's the n equals 2 level, that's here. Okay, there's the n is equal to 3 level, there's the n is equal to 4 level, there's the n is equal to 5 level, and so on. Okay. All right, and what Pascal showed was that if you wanted to compute the kth entry of the nth row, this is computed by this symbol n minus 1 k minus 1, and the way that we read this typically would be n minus 1 choose k minus 1. So let's do a little aside here, right? So a little aside here. So an aside. So when we write this symbol, what do we mean here? So this is, does anyone remember how this goes? This is n factorial over k factorial times n minus k factorial, right? Does anyone remember what that's called? And this ties in with something that I'm going to mention here in a second. So, does anyone remember what they call that. And the name of it that you probably know is something that kind of gives away why this is so nice. So anyway, this is called the binomial coefficient. So I will write this in a second. This actually gives away why it's so good, but this is the binomial coefficient. The way that this is said in probabilistic settings or combinatorial settings is this is called n choose k. What does that mean? This means that it is the number of ways to choose k objects from a set of n total objects. All right? So here's a quick, just kind of quick computation to verify this is what's happening. Let's say that, so to remind you, of course, factorial, right? If I write n factorial, what is that? That is n times n minus 1 times n minus 2 times n minus 3, and so on, all the way down to 3 times 2 times 1. Right? This is n factorial. Okay. And of course, we define 0 factorial to be 1. Okay. So this tells me the number of ways to choose k objects from a set of n total objects. So let's say that I have 5 different colors, right? So red, black, white, green, and blue. Okay, so I have 5 different colors. I want to know the total number of ways, right, or the total choices, the total pairings that I can get from that 5, right? So I want to know the total number of ways that I can choose 2 of those colors from that total of 5 colors. So that would be 5 choose 2. What is 5 choose 2? So 5 choose 2 is 5 factorial over 2 factorial times 5 minus 2 factorial, which is 3 factorial. So that's 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. So those get canceled, and I'm left with 20 divided by 2, which is 10. There are 10 ways of doing that. Okay, and so you could probably quickly list what those color combinations are very quickly. Okay. All right, so that's just as an example to remind you. Most of you have seen this in some form before. Okay, and so it won't surprise you then, knowing this and knowing that Pascal was the first to work out the property of Pascal's triangle, that actually these things that are being computed is exactly these binomial coefficients, right? So the entries of Pascal's triangle are the binomial coefficients. All right, this n choose k business. So knowing that he was the first to work this out and write this down explicitly, it won't surprise you to know that Pascal was also one of the first to work in probability. Okay, so I'll mention that again here in a little bit. So he also worked out, since he explicitly said that the entry of the table of the kth entry of the nth row is n minus 1 choose k minus 1. He also worked out that n minus 1 choose k minus 1 could also be expressed as n minus 1 times n minus 2 all the way down to n minus k plus 1. That's n minus k minus 1 all over k minus 1 factorial. Okay, which is an alternative way of writing the n choose k formula, right? So this is actually the same as this, right? Just plug n plus 1 into this and you get the same thing, right? Okay. No, bins, they're not taken one at a time. They're taken all at once. Yeah. So the way that this choosing goes is that you're taking 2 at a time. You're not taking one and then another one. You're taking 2 at a time. That's how the wording of these goes. Okay. The way that, although it's an interesting question if you want to think about whether it matters and how it matters, that is whether we went with the other alternative here. Okay, so he also worked out, so Pascal also showed the following formula, which is that n choose k can be rewritten as n minus 1 choose k plus n minus 1 choose k minus 1. This fact is another way of easily generating this table recursively. And so this is like the recursive form of Pascal's triangle, so that you could generate the whole table just from this. So this is basically, if you wanted to quickly write some very simple program to generate an entry in Pascal's triangle, this is an easy way to do it. The most important thing, however, is the following. So Pascal showed that the entries n choose k, right, compute the coefficient of x to the k, y to the n minus k in the binomial expression x plus y to the n. Thus, the name binomial coefficient. What do we mean here? Okay, so let's do a quick example. Okay, so quick example. If I wanted to do, say, x plus y cubed, right, how do I do that? Well, I could do this as x times y, or x plus y times x plus y squared. Squaring is easy enough, I know how to do that. So this is x plus y times x squared plus 2xy plus y squared. Right? And now I have to do this product further. So I'm going to multiply x by everything. So that's x cubed plus 2x squared y plus xy squared. Now I'll multiply y by everything, plus yx squared plus 2xy squared plus y cubed. Right? And now finally, I simplify here. I have x cubed. I have 2x squared y. Do I have another x squared y showing up here? Yeah, here's an x squared y. So I have plus 3x squared y plus xy squared plus 2xy squared. So that's plus 3xy squared plus y cubed. So finally, I'm done. Okay. Well, what did I do here? I could have looked at x plus y cubed, gone to the n equals 3 layer. Since Pascal showed that n choose k computes the coefficient of x to the k, y to the n minus k in this binomial expression x plus y to the n, and x plus y cubed, then I could compute every single one of these. The coefficients are 1, 3, 3, 1. Hey. Right? This saves me a lot of work. So let's do this for n equals 5. All right, so let's use Pascal's triangle to do this for n equals 5. So let's expand x plus y to the 5th. Now that would be awful if I was doing that in the brute force way, but using Pascal's triangle, the coefficients arranged from x to the 5th to y to the 5th are 1, 5, 10, 10, 5, 1. So what is this? This is x to the 5th plus 5 x to the 4th y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 xy to the 4th plus y to the 5th. So Pascal's triangle and the fact that those entries are the binomial coefficients in this binomial expansion, this makes it a lot easier to expand things like this. All right, so it saves a lot of time. And of course, there need not be a y here. This could be x plus 2, right? And then you'd put 2 everywhere y shows up. All right, so this gives you a very quick way of doing this algebra that would be really, really tedious otherwise. Okay, so this is really, really nice. And so if you have ever seen the Binomial Theorem, right, that is essentially what has been shown here, right? That the Binomial Theorem, which tells you exactly how to expand x plus y to the n, is given by Pascal's triangle. So he showed that. Okay, so both Fermat and Pascal dealt with probability, and after you saw this and the relationship between these entries in Pascal's triangle and this n choose k action, and if you take a class again in probability, of course you've probably already seen this, but if you take another class in when you're doing basic probability stuff, this comes up a lot. Okay, so being able to compute or computing binomial coefficients, this is something that comes up very often in probability, so it's not that surprising that Pascal was very closely involved with the very beginnings of probability, like the mathematical study of probability. And in fact, you might also be aware that he used this his interest in probability to put forth this philosophical thought experiment that bears his name, that you've probably heard, which is called Pascal's wager. Okay, so what was the idea behind Pascal's wager? Pascal's wager was that if you were approached by someone and they made you aware of, say, some religion or some religious belief, and in this religious belief there was an infinite reward to be had if you believed in God, right? So belief in God would yield an infinite reward potentially in the future. Now, of course, if you're a skeptic, maybe you're like, well, I think the probability that that's true is really low. But Pascal, says if you admit that that probability is not zero, if it's a positive probability, right, of this being true, then even if it's small, because the reward offered to you, if you believe in it, is infinitely large, right? It is infinitely positive. Okay, then basically it doesn't matter how small that probability is, if it's still a positive probability, if it's still greater than zero, then the fact that there's infinite rewards for believing in it should make you believe in it, right? Now, of course, this kind of ignores how belief works, and that it can be kind of hard to just switch. Belief is not typically a light switch. You can just switch one way or the other. And also, as the textbook notes, which is pretty funny, it's whether or not Pascal considered the possibility that a deity might punish those who adopt beliefs in expectation of personal gain, right? So you're walking around living your life, and someone approaches you with this knowledge, and you're like, yeah, okay, I live the rest of my life this way, but now that I see there's something in it for me to gain, I switch, right? So that wasn't really discussed. There's another, so regardless of what you think of Pascal's wager, there's a very similar argument that was brought up much more recently. I think it's not even 20 years old. It's a thought experiment called Pascal's mugging, which is very similar in its argument. And Pascal's mugging is the original thought experiment was someone comes to you and says something to the effect of basically the entire universe will be destroyed tomorrow if you don't give me $5 now. And the way that the argument works is that even if it is extremely unlikely that this would happen, the downsides are essentially infinite. That is the destruction of everything, of all that is the universe. And when the downsides are essentially infinite, basically it is kind of the morally justified thing to give up your money in this scenario, because even if it is almost certain that you're not having no effect, the potential for infinite bad is so great that it is still enough to warrant you giving the money. So that was the original formulation of it. Now, where this comes into play in thought experiments about like ethical donating of money is the following. So you can recast Pascal's wager like this. So you don't have to imagine this. It is just looking at the history of, say, Earth. There's been several instances of catastrophic mass extinction events, right? So that are most of them, not all of them, but many of them related to impacts with various celestial bodies, right? So giant asteroids impacting, giant impactors hitting the Earth and destroying a huge chunk of life on Earth. And you might say that, forgetting about other various ways the solar system or the Earth could come to an end, the chance that, there is a significantly high probability as you take the time to infinity, as you think further and further and further into the future, that there will eventually be some giant bolide impactor that will impact Earth and destroy everything. Okay, so that's not only is it not that crazy of a belief, it's almost a certainty, just given the past distribution of these types of events. And anyway, so if you admit that's almost definitely going to happen, of course this might be billions of years in the future, but this will eventually happen. The idea is that the chance of this happening, tomorrow is very, very small, right? And the chance of it happening next month is also very, very, very small. But it's small, but it's positive, right? It's a tiny positive amount. But the downside is huge, right? Namely mass extinction. Okay, so here's where the problem comes in. Say you go to, you want to donate, right? You want to donate your money to some like local charity organization. Someone comes to you and says, well, that's great, but like how much is your money really helping this local charity organization, right? In the greater context of things, isn't your money more ethically spent on this infinitely bad problem, right? So wouldn't it be better to put your money towards like asteroid deflection technology, right? Because like nothing is more dangerous than this. Similarly, you'll see this argument for like AI safety, like artificial intelligence safety research and technology is where this is typically used. So basically, the main idea is use existential threat to mug you of money, even if like this existential threat has a tiny, tiny, tiny chance of happening. The idea is that because the downside of it happening is so large, basically it is unethical to spend any money preventing any other ill except that thing. Because, right, if that thing occurs, it's way worse than, anything else that you're trying to prevent from happening. Anyway, so if you see Pascal's name thrown about in those kinds of arguments, that's exactly why. Because he himself came up with this Pascal's wager that was very similar in tone. Okay, so anyway, moving on from just exclusively French mathematicians of the 17th century, there were plenty other very important 17th century mathematicians. I might need a new list here. So 17th century, not necessarily French mathematicians. Are any French mathematicians on this list? No. So 17th century mathematicians outside of France. I'm going to add in some that the textbook ignores just because I want to be able to have a good story. So the first that we're going to talk about is Bonaventura Cavalieri. I'm going to try my best to not spoil anything that these people did until I talk about them. So he lived from 1598 to 1647. He was Italian. Next, John Wallace was English. He lived from 1616 to 1703. He was English. Nicholas Mercader. This is not of the Mercader projection fame. So Nicholas Mercader. So not the map guy, I'll say. Okay, the map guy lived a little bit. He lived like 50 years earlier. 1620 to 1687, and he lived in Germany and England. Christian Huygens. So he lived in Holland, 1629, 1695. The next, Isaac Barrow. I'm not going to say that much about him. James Gregory. Lived from 1638 to 1675 in Scotland. Next is Isaac Newton. Who lived from 1642 to 1727 in England. Next is Leibniz. So he lived from 1646 to 1716 in Germany. And I wanted to add in, I'm going to add here as a number 9. You'll see why I'm treating this separate. So the textbook doesn't actually mention them, but I wanted to at least mention them because it's kind of hard not to mention them. So I'm going to mention Johann Bernoulli, who lived from 1667 to 1748. He had a brother, Jacob Bernoulli. There was an entire clan of Bernoullis, so plus Bernoulli clan. So some in the mid 1700s did a lot, plus Bernoulli clan. If you're interested in all of the Bernoulli family, there's a ton of them that you can look up on Wikipedia. Many of them were mathematicians or scientists of some type. I'm specifically going to mention Johann Bernoulli for a particular story, but Johann and Jacob were contemporaries. They were brothers, and they were contemporaries of Newton and Leibniz. And so they did a lot of stuff, but if you want to see the specifics, I'm going to include it in an update to the info dump. Okay. So this is my massive list. All right. So just starting at the top here, Cavalieri. What did he do? So Cavalieri was the first person to compute areas under curves that exceeded Archimedes, basically. So what did he do? So one, he rediscovered Archimedes' method of indivisibles. For computing area. So he used this to compute the area of an ellipse, for instance, which is pi AB. He's not the first person to do that. I believe even Archimedes had essentially done that, but I think Apollonius actually is the one that did this, so rediscovered the fact due to Apollonius. that the area of an ellipse with major and minor axis length A and B is A is equal to pi A B. Okay. So the way I'm defining this length is if you take it as the actual length, it would be half that. But yeah, here's the statement. So this is due to Apollonius, but Cavalieri rediscovered this. The most important thing that he did is Cavalieri's formula. It is the first thing that moved beyond Archimedes' computation of area, and it is technically the first calculus thing that was done. Okay, so this is kind of the beginning of calculus, and what was done is the computation of the area under the curve x to the n. So written in modern notation, this would say that the integral from 0 to a of x to the n dx is a to the n plus 1 over n plus 1. So there's another number of ways to recast this. Okay, a number of we can view this in various different lights. So one, this is the power rule for integration. Okay, so that's one way of putting this. Okay, this is the first, we'll say, calculus fact. So this is like the very beginning of calculus here. This computes the area under the curve y is equal to x to the n. All right. So Archimedes was only able to compute areas under parabolas using this trick, but this allows you to do not under just parabolas, but areas under cubic, quartic, and quintic powered things here. And I should write out what I had just said in words, that this is the first time Archimedes' method is surpassed, specifically in computing areas under curves. Okay. So, and you can just count the years, right? This means that Archimedes was like 1,800 years ahead of his time or something like that. All right, so this is pretty amazing. Okay, but this is exactly what it says. Okay, and that's why it's important. All right. If you really want to impress your friends, they show you, they try to use the power rule, you can call it Cavalieri's formula and confuse everybody. Okay. Wallace. So John Wallace is an English mathematician. He was a professor of geometry at Oxford. He was a staunch royalist. He actually became chaplain to Charles II after the Restoration. So he had a couple of innovations. So in algebra, he was the first to use negative exponents and fractional exponents. So he used negative and fractional exponents. So, for instance, when he would write x to the minus n for some positive integer n, this was the same as 1 over x to the n, right? Just like we do it. And if he had x to the p over q, where p and q are two integers, then this was written as the qth root of x to the p, just like we do it. Okay, so he introduced this notation as far as I'm aware. Okay. He used Cavalieri's method to repeat Cavalieri's results for more general expressions, in particular for polynomials. So he used Cavalieri's method to compute areas under polynomial curves. So he was able to do this for a general polynomial. So if you let y be equal to, a naught x to the 0, so that's your constant term, plus a1 x to the first plus a2 x squared all the way up to a sub n x to the n, he could compute the area under any polynomial curve like this using Cavalieri's method. Okay. We, of course, know now that this follows directly from what's called the linearity of the integral, right? So integrating an expression that is a sum of expressions, you can break that up across the sum, right? We also know that it's linear in the sense that you can pull constants outside of the integral. And so knowing those two algebraic facts, this would have followed for us immediately, right? If the second you see Cavalieri's formula, you can do this, but Wallace was the first to do this. He also discovered this funny expression for pi as an infinite product, but he couldn't actually give a rigorous proof for this, but he did give this expression that pi is 2 times 2 over 1 times 2/3 times 4/3 times 4/5 times 6/5 times 6/7 times 8/7 times 8/9, and so on. So this is pi is an infinite product. He couldn't show that this is the case, but it is indeed the case. So he couldn't show that this thing actually converged to pi, but it does. Okay. All right. What about Mercader? So again, this is not the map guy. So he computed the area under the curve y is equal to 1 over 1 plus x. Huh. How did he do that? How did he compute the area under this curve, right? This is not a polynomial, right? This is a rational expression. How did he do this? Well, he viewed this as a kind of polynomial. We have better words for this, and you can type it in the chat if you realize what I'm about to say. So if y is 1 over 1 plus x, there's another way to view this. You can view this as this infinite polynomial, 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th, and so on. But it's an infinite polynomial. Well, what do we call an infinite polynomial or an almost polynomial or kind of polynomial? What's the name we have for this? So if no one types it in a few minutes, I'll write it out. But he used this to obtain a particular way of writing the natural log, that is the log base e of 1 plus x. Yeah, Ben. So it's a power series, right? So this is these almost polynomials are infinite polynomials. These are power series. So what's awesome about power series is that they take a thing that is not a polynomial and allow you to write it as something that behaves like a polynomial. It's just a polynomial that's of infinite degree, right? So if you have something that you can do term by term, you're pretty happy with a power series. Now, there's questions about convergence, but at this point in mathematics, the mathematicians did not worry terribly much about convergence. So they did some computations that were a little bit iffy. Okay, they didn't worry too much about convergence. And so, anyway, the idea here was, yeah, you could basically treat these like polynomials. So from this, he obtained the natural log. So in computing the area, this is actually one of the ways you can define the natural log. In fact, if you took Calc 1 through 3, if you took any of those at UMD, this is how that textbook defines the natural log. And so he obtained here an expansion, a power series expansion for the log base e of 1 plus x, and found that this is x minus 1/2 x squared plus x, 1/3 x cubed minus 1/4 x to the fourth, and so on. So he obtained the power series expansion for the natural log. Now this only converges for x between 1 and minus 1 because of this 1 plus x, the shift that's going on. Okay. So it was later that Gregory of St. Vincent showed. This is the nice power series expansion for the natural log, but to think of the natural log as the integral of 1 over x, that is due to this Gregory of St. Vincent, who lived from 1584 to 1667. First showed that the integral of 1 over x dx is equal to the natural log of x. Okay. Which is the power rule that Cavalieri, I should say, I neglected to mention this when we mentioned Cavalieri's formula. This works for every n except minus 1, right? So when n is minus 1, this is a 0 in the denominator, so that's bad. So this works for every exponent except n equals minus 1. Wallace allowed us to express x to the minus 1 as 1 over x, and so Gregory of St. Vincent was the first to actually show that this plugs the only hole in Cavalieri's power rule formula for integrals. Okay. All right. Now, Huygens is probably more known for his scientific achievements. So, namely, he is the one who came up with the wave theory of light. So, if you're interested in a history of that, you should look up like the wiki article for Huygens. I don't actually know a good book that maybe discusses this. So his wave theory of light was kind of discarded due to everyone kind of adopting Newton's treating light as, particles. But it wouldn't be until you get to the late 19th century, early 20th century, when you have quantum mechanics, that this treating light as wave was something that was thought of seriously again. And this went all the way back to Huygens. So anyway, kind of the most significant mathematical thing he did was he studied cycloids and their evolutes. Okay. Which are also cycloids. So the cycloid is a curve whose own evolute, I'm not going to define what that is. So there's evolutes and involutes of curves that can be defined. These are very interesting because these are, you get these nice kinematic or like motion defined curves in the plane. There's a lot of really beautiful examples of that kind of thing. So he studied cycloids and their evolutes. It turns out that the evolute of a cycloid is another cycloid. This has to do with, so studying the motion of pendulums, oscillatory motion, cycloids come into play. The main place I want to talk about cycloids is in this story that I want to tell. Well, maybe I'll tell the beginning of, or maybe I'll tell the story at the beginning of next lecture, but that's when so maybe I'll stop here. I'll talk about cycloids later when we discuss this on Monday, because there's a nice story about a problem that was sent to all mathematicians of Europe, and Newton was so annoyed by the problem that he decided he would stay up all night and work out the solution in a single night, and then mail his solution to Johann Bernoulli, which is what he did. So I'll talk about that at the beginning of the lecture next time. So until then, I will see you all later.